Hi guys, we are starting chapter 11, which talks about reactions. Chapter 11 is my absolute favorite chapter. I think it's awesome because at the end of this chapter you are going to be able to look at two different substances and know how do they react together, what type of reaction, predict what the products are, write an equation for the reaction and balance it. So I think this is the chapter where you actually become real chemists. So we're going to start the chapter by looking at some different things that you find in a chemical equation that describes a reaction. So in an equation, you'll see that you have two sides separated by an arrow. The left side, of course, are your reactants. Sometimes you have one reactant, sometimes you have two, sometimes you have 100. It depends. And then the product side, same thing. It's on the right side. And you can have one product or two products or three products or however many. Separated, the reactants and the products are separated by this arrow here. So the reactants are the ones that are on the left side, and those are your starting materials. And products are on the right side, and those are what you end up with, your end result. Or your ending materials, I guess. They are separated by an arrow. This is what we call yields or produces. So when we are reading this equation here, we'd say A reacts with B to yield or to produce or to form C and D. So that arrow means yields or produces or forms. Sometimes that arrow is just going to be a regular one-sided arrow. Sometimes you'll see two arrows on top of each other. If you see two arrows on top of each other, that means it's a reversible reaction. So reversible reaction, just like a reversible jacket can go both ways, reversible reaction can go both ways. RXN stands for reaction. So most of the reactions are actually reversible. So that means that the reactants react together to form the products, but then the products can react together to reform the reactants. There are a few reactions that are not reversible, but the majority of reactions are reversible. We're going to look at that when we get to second semester in chapter probably 18 or so. Sometimes you'll see your arrow with the word cat on it or with a substance here, like MnO2 or something like that. That means that a catalyst is added to the reaction. And so you either write cat for short or the word catalyst on the arrow, or you write the formula for that catalyst on the arrow. But this means a catalyst is added. And we're going to talk about catalysts again later on, but catalysts are substances that speed up the reaction without being consumed. Sometimes you'll see the arrow with H nu on top. If you remember back in chapter 5 when we talked about electrons and light, H nu was equal to energy. And so this means that energy is added typically in the form of light energy. So something like photosynthesis, you would see H nu on top of the arrow. So light energy is added. Sometimes you'll see the arrow with a triangle on top. That means that energy in the form of heat is added. So this is heat. Energy added. Some reactions you need to heat up in order to get them to react. Sometimes you'll see your substances with a little G in parentheses, or a little S, or an L, or an AQ, or a downward arrow, or an upward arrow. So these are all symbols that you see at the end of a substance. So for example, you might see your substance is H2O with a little L next to it, or a little G next to it. So G stands for gas, that means your substance is a gas. S stands for solid. L stands for liquid. AQ stands for aqueous. And some people pronounce it aqueous, some pronounce it aqueous. It comes from the word aqua, which means water. And so this means that it's dissolved in water. So a lot of our salts, our solids, can't react by themselves as a solid because in order for a reaction to occur, you need collisions to happen, and so solids just vibrate in place, and so it's harder for them to collide. And so what we do is we dissolve our solids in water to make a solution, and once they're dissolved, the ions are able to move around a little bit more and collide more so that you can get a reaction. If you see a downward arrow, that means a precipitate formed. Precipitate, which means a solid. So you combine two solutions, and then one of your products is a solid that's insoluble, so it precipitates down. So you put a downward arrow next to your product. Up arrow means a gas is formed. So when you combine substances and you form a gas, the gas, bubbles up and goes out. And so that's why an up arrow represents a gas that is being formed. So let's look at a reaction here. It says solid magnesium reacts with aqueous hydrochloric acid to yield hydrogen gas and aqueous magnesium chloride. So let's try to write our balanced chemical equation here. So solid magnesium is Mg, and solid, we would put an S next to it, reacts with, so plus aqueous hydrochloric acid. Hydrochloric acid would be HCl. And it says aqueous, that means it's dissolved in water, so we put AQ. To yield, so arrow, hydrogen, which is H2 because it's diatomic, and it tells us it's a gas, so G, and aqueous magnesium chloride. So magnesium chloride is MgCl2, and this is aqueous. So you can see that a lot of chemistry builds on itself, and so you need to know Chapter 9 nomenclature in order to be able to do this well. Now, the problem here is that the way that this reaction is written, that defies the law of conservation of mass. For example, here we have 2 hydrogen atoms, but here we only have 1. Here we have 2 chlorine atoms, and here we have 1. So that cannot be true. It cannot exist. We can't defy the law of conservation of mass. You can't create or destroy matter. And so we have to balance chemical equations. So when we balance them, we use coefficients, and the coefficients go in front of the numbers here. And so we would need to put a 2 right here so that it is balanced. If there is no number in front of your substance, that means that that's a 1. So 1 magnesium plus 2 HCl yields H2 plus MgCl2. When you read, like when I ask you to balance a chemical equation and ask you to, tell me what the answer is, you read the numbers of the coefficients. And again, if there's no coefficient, that's a 1. So I would tell you, like if I ask you, how do you balance this? You tell me 1, 2, 1, 1. That would be your answer. So mass can never be destroyed, of course, and so your number of atoms on both sides need to be equal. Coefficients in a chemical reaction could mean particles, or they could mean moles. So you could say 1 magnesium atom is reacting with 2 molecules of HCl to produce 1 molecule of H2 and 1/4 unit of magnesium chloride. So that would be particles. Or you can say 1 mole of magnesium reacts with 2 moles of HCl to produce 1 mole of H2 and 1 mole of magnesium chloride. In a chemical reaction, mass is conserved, which means number of atoms. Particles are not conserved. Molecules are not conserved. And so if you look at this, there are 3 moles or 3 particles on this side, and there's only 2 on this side. So molecules and particles in general and moles are not conserved in a chemical reaction necessarily. but the number of atoms are conserved. Okay, so let's try to practice balancing chemical reactions. Some of you have done this last year or previous years in your other science classes, and this comes naturally to you, and it's pretty easy. For some of you, you haven't really done it very extensively, and so it's really hard. So just practice as much as you need to. So if you feel like you know how to do it, then that's great. You need minimal practice, but if you feel like you need a lot of practice, then make sure that you do lots of worksheets and extra practice and all that. So we're not going to use our molecular models, but we are going to draw particle diagrams because I think sometimes that helps. So I'm going to go ahead and draw a particle diagram for H2 here. And so I have an H and another H. Cl2 looks like this. And so I want both sides to match. So I'm going to start by drawing one of each. And as you can see here, I have 2 hydrogen atoms and 2 chlorine atoms. One here, I only have one of each. So I need to add one more HCl. And so that balances it out. I have 2 H's and 2 Cl's on both sides. And so I need to make that a 2. So it's 1, 1, 2. Go ahead and make my pen a little lighter. Let's do number 2 together. So I have H2, O2, and I'm going to form H2O. And so you can see that my oxygens are not balanced, so I need to add one more water here. But now my hydrogens are not balanced, so I need to add one more H2. And now it's balanced. So 2, 1, 2. Let's look at number 3 here. So N2. F2. And then we have an F3. And so my nitrogens are not balanced, so I need another NF3. And so that balances my nitrogens, but my fluorines are not ready or not balanced, so I'm going to make 2 more of these. So now it looks like it's balanced. I have 2 nitrogen atoms and 6 fluorine atoms. And so I need 3 of these, 2 of these, and just 1 of the N2s. Try number 4, so pause the video and then play it again and look at the answer. So it's going to be 1CH4, 2 O2s, and then we're going to form 2 waters, and 1 CO2. Okay, next that we're going to do the same thing. We're going to balance it and draw particle diagrams. So let's go over a couple of tips here. Let's look at number 7. So one of the tips here is that if you look at the oxygen, here you have 3 and here you have 2. Whenever you have 3 and 2 of something, one side has 2, one side has 3. A trick to this to make it a little bit faster is that you put a 3 in front of the 2 and a 2 in front of the 3. So you have a total of 6 oxygens on both sides, and then you balance the rest. So my potassium, I need 2 there. My chlorines are balanced. Another tip is if you have polyatomic ions If you want, as long as they appear on both sides, like see how here there's a nitrite and a nitrite, a sulfate and a sulfate. If you would like, you can treat it as one big thing, as opposed to breaking it up into nitrogens and oxygens and sulfurs and oxygens. You can think of it as one nitrite or two sulfates or something like that. So let's do this one together. So I'm going to start with my sodium. So on my product side, I have 2 sodiums. On my reactant side, I have just 1. So I'm going to make that a 2. Let's look at my nitrites. So I have 2 nitrites here, 1 there. So I'm going to make this a 2. My sulfates, I have 1 here and 1 there. So that's good. And then my hydrogens, 2 hydrogens and 2 hydrogens here. So this should be balanced. Another tip is that if you, so let's look at this one here. This one, you can't really treat the hydroxide as one big unit because you see hydroxide here, but no hydroxide here. You'll see that you have lots of hydrogens and oxygens here. I would keep things that appear more than once on a side last. So if I'm doing this, I would balance like the nickel first, and I'd balance the sulfur first before I go balance the hydrogens or the oxygens. I would do those last. So you want to do the ones that only appear once, first, and then you do the other ones. So let's do this one here. So 1 nickel, that's good. 1 sulfur, that is also good. Let's look at the oxygens, 2 here and 4 there, so that's 6. On the side, I have 4 and 1, so that's 5, not 6. And so this number is even number of oxygen. Here I have an odd number of oxygen. Whenever you have odd and even, what I would recommend is double whatever's making it odd. Make it even. So this is an even number of oxygens. This is an odd number of oxygens. So I'm going to double this right here. That way, now I have an even number of oxygens. So 6 oxygens and 6 oxygens. And then the hydrogens, let's do that at the end. So 2 here and 2 here, that's 4, and 4 here, so that is balanced. I also recommend that you make a list of all the different atoms that you have. So like if I were doing this, I'd list nickel, sulfur, oxygen, and hydrogen. And as I go through, I kind of either check it that it's balanced, or you might want to make a list. So like 1 on this side, 1 on that side, sulfur's 1 and 1, oxygen 6 and 6, hydrogens 4 and 4. So making lists sometimes helps. Also drawing particle diagrams also helps. So I'd like you to stop the video now and then work on 5, 6, and 10. Those are the ones that we left out from here. Also draw your particle diagrams again. Sometimes that helps a lot. And then play the video when you are ready to go over the answers. So let's go over number 5 together. Hopefully you did these already. So 1 barium, 1 barium. I'm going to make a list here for myself. Chlorines, potassiums, and iodides. So 1 barium, that one's good. Cl, so 2 here on the reactant side and only 1 here on the product side. So I'm going to make that a 2. So my bariums and chlorines are good. My potassium, I have 1 here and 2 here. So I'm going to put a 2 here. So that one's good. And then my iodide, 2 here, because there's a 2 there, and then 2 here, so that's good. Now, once you change one thing, make sure you go back and look at the other ones in case they've changed. So always check at the very end after you've written all your coefficients. So bariums, 1 and 1, chlorines, 2 and 2, potassium, 2 and 2, iodides 2 and 2, so everything's good. Let's look at number 6. So calcium 1 and 1, that's good. We also have oxygen, oxygen 2 and 1, so that's not good, so I need to make this a 2. So my oxygen is good, 2 on each side, but then now that I changed this, I've changed my calcium. So now this is 1 and this is 2, so I'm going to make this a 2. And so now both are good. Let's look at number 10 here. So magnesium, there's 3 here, so I'm going to make this a 3. Nitrogen, so this is a 2, so I'm going to put a 2 here. So we got magnesium, nitrogen, hydrogens, and oxygens. So magnesiums are good, nitrogens are good. Let's go to, I'm going to do the oxygens first, because the hydrogens here appear in 2 places, but the oxygen only appears in 1 place on either side. So I'll do the oxygen first. So 1 oxygen here. Here I have 2 times 3, that is 6 oxygens. So I'm going to go ahead and make that 6 waters to balance out my oxygens. And now let's look at the hydrogens. So here I have 12 hydrogens. On this side I have 2 times 3, which is 6, and then 2 times 3, which is 6, 12. And so that checks as well. All right. Next, I would like you to work on 11 through 16. Again, stop the video, work on them, see how you do. Give yourself a chance to do it by yourself, and then play the video, and I will walk you through each of them. So hopefully you've worked on these. Let's start with this one. So nitrogen, 2 and 1, so I'm going to make this a 2. And then my oxygens, 2 and 2, so that one's good. Next one, I see iron and oxygen, and I see that this oxygen has a 2 and this oxygen has a 3. So remember, my tip was to put a 2 in front of the one that says 3 and a 3 in front of the one that says 2. So my oxygens, I have 6 and 6, so that's good. My irons, I have 1 and 4. So I'm going to make this a 4. Let's look at number 13. So potassiums, I have 2 here and 3 there. So again, my trick is to make this a 3 and this a 2. So I'm going to go ahead and list these. I have potassium, I have aluminum, and I'm going to list the carbonates and the phosphates are as one big unit as opposed to breaking them up into phosphorus and oxygen or carbon and oxygen. If you would like to break them up, that is fine as well. But because I see them on both sides, that is okay to do that. So I got my potassiums to balance. I have 6 on each side. Next, I'm going to do my carbonates. So 3 carbonates, so that one's good. Aluminum, I have 1 here and 2 there, so I'm going to put a 2 here. And then phosphates, I have 2 here and 2 here, so that one's good. So always, when you've done one and then you've changed the coefficient, go back and double check. Potassium still good with 6, carbonate still good with 3, aluminum still good with 2, and phosphate still good with 2. Let's look at number 14. So let's make a list here. We have lead. We have nitrates, we have lithium, and we have phosphates. So let's start with the lead. Here there's 1 and here there's 3, so I'm going to make this a 3. Nitrates, I have 2 times 3, which is 6. On this side I just have 1, so I'm going to make this a 6. My lithiums, I have 3 here and 6 there, so I need to make this a 2, so that I have 6 on both sides. And then my phosphates, I have 2 and 2, so that's good. So let's double check. Lead, 3 and 3. Nitrates, 6 and 6. Lithiums, 6 and 6. And phosphates, 2 phosphates and 2 phosphates. checks out. Number 15, silver nitrate combines with tin 2 chloride to form silver chloride and tin 2 nitrate. So this is a word problem. So let's start with silver nitrate. Silver nitrate is ionic, so I need to balance out my charges. So silver ion is +1, nitrate is NO3 minus, so silver nitrate is AgNO3. Combines with, so that means I'm going to put a plus, tin 2 chloride. So tin 2 means it's SN with a 2 plus, chloride is Cl minus, so SnCl2. To form, so arrow, silver chloride, so silver is Ag plus, chloride is Cl minus, so AgCl. And so plus tin 2 nitrate, so SN2 plus is tin 2, nitrate is NO3 minus, so SnNO3 2. So you use your subscripts to write neutral compounds like we've done now, and now we're going to use coefficients to balance. So silver 1 and 1 for now, nitrate 1 and 2. Oops, so I need to make this a 2, which changes my silver. So now 2 silvers and 1 silver, so I'm going to make this a 2. Tin 1 and 1, chloride Cl2, so 2 here and 2 Cl, so that's good. So let me make a list again of the different things that I need to balance. All right, so silver 2 and 2, nitrates 2 and 2, tin 1 and 1, and then chloride 2 and 2. So that one's good. Last one here, magnesium and chlorine react to produce magnesium chloride. So magnesium is Mg. Chlorine is diatomic, so it is Cl2. Don't forget your 7 diatomics. To produce, so arrow, magnesium chloride. So Mg2 plus and Cl minus, magnesium chloride is MgCl2. So my magnesiums 1 and 1, my chlorines 2 and 2. So that one's already balanced. All right, hope you guys have a wonderful day. Practice balancing equations with your worksheets. Bye.